దేనికి అబ్బా నిద్ర వస్తుంది. ఎక్కడికి?
Hello students, good evening all. So welcome back to our next session of chapter linear inequalities. So first we'll just have a quick recap of so far what and all concepts we have discussed, and we'll just have a quick overview of today's concepts that we have to discuss in our today's session of linear inequalities. So in our previous sessions, as I mentioned, the most important method which we have discussed in our linear inequalities is nothing but wavy curve method. And we have seen first what and all conditions which we require to apply this wavy curve method for any given inequality. So there are list of conditions first we have to check, and after verifying the conditions, then we have to follow the working method or the methodology of our wavy curve method to find the solution of the given inequality. And along with this wavy curve method, we have even discussed the modulus inequality. So we have even seen the working method in specific for the modulus inequality also, and we have solved questions with respect to the modulus inequality. Right, so these are the two important things which we have covered so far in our linear inequalities. And before that, we just had a discussion about our basic properties and what and all the conditions which we have to keep in mind while solving these types of inequalities or our wavy curve method and these and all. Right, so coming to our today's session in specific, so what and all topics we are going to cover here. So today we are going to start with square root inequality. Right, so if you guys remember, while discussing the basic properties of inequality, we have discussed that we can't simply square on both sides for any given inequality unless if we are sure that both sides of the inequality is a positive value. Right, so that condition will be coming into picture when we are solving any square root inequality. Right, so here today's session we are going to start with our square root inequality, and we'll be seeing what will be the corresponding condition which is required, as I mentioned, which are from our basic properties. We'll be inheriting that, and we'll be seeing the working method to find the solution of any given square root inequality. So after that, the next important inequality which we are having here is logarithmic inequality. So we'll be knowing that for any logarithmic inequality, for any logarithmic thing, the base of that logarithmic equation or the expression will be very, very important. Right. So even in our inequalities, the base of the log will be playing a crucial role here. So depending upon the base here, we'll be checking whether the inequality of the expression will be changing or not. Right. So as in the same typical manner, even for the exponential inequality, because they are similar to each other, it's like inverse of the others. So both for logarithmic and exponential, we'll be having similar conditions here. Right, so for logarithmic, it will be the base, and for exponential, it will be the power. So we'll be checking what and all conditions, and where will be the inequality will be changing, and where will be the inequality remain constant. Right, so that and all we are going to discuss. And last but not the least, the final inequality we are going to discuss, which is very, very important again, that is nothing but our trigonometric inequality. Right, so as you can see here, the concept itself, trigonometric inequality, which is related to our trigonometric functions. So if you guys remember, we have discussed the graphs of our all trigonometric functions, like for sine, for cos, for tan, how it will be the graph of the trigonometric function. Right, so here to solve any trigonometric inequality, we are going to bring those graphs here, and we are going to solve this inequality using the graphs of our trigonometric functions. Right, So this will be our last concept in our linear inequalities. So today, as in overall, we are going to cover 4 important inequalities in our today's session of linear inequalities. The first will be square root, and then logarithmic, and then exponential, and then trigonometry. And for each of it, we are going to solve the corresponding questions also. Right, so without any late, so let's get started with our today's session, guys. So as I mentioned, first we are going to start with the square root inequality. Right, so for square root inequality, it will be easy when we actually solving the question and doing it. Right, but before getting into that part, I'll just give you a quick tips, like quick starting points, how we actually do it for our square root expression. Right, so if for suppose we are having some square root expression here and greater than or equal to something square root expression y. Right, so or else we could have some x greater than square root y. Right, so if this is the case, as here they are given in terms of variables, we are not sure that whether x is greater or y is greater. Right, we are not actually sure here. Right, which means it can be negative value this side, it can be negative value this side. Right, so if that's the case, it cannot be negative also. So if for suppose if you take x equal to 4, then y can be some 8 here or else 16, then will be 4 greater than 4 is not possible. Right, so depending upon the values which you are taking, it will be differing. So that's why we cannot actually square. So for suppose let me take some x equal to 4 and y equal to some 25. Right, so if I take x4 and y is 24, in the sense root 5, root 25 will be 5, that means 4 greater than 5. Is it possible? No, right? So 4 greater than 5 is not possible. So let us take another example here. So let me interchange the thing, do it this way. So x less than root y. Right, so let me take x equal to 4 and y equal to 25. So then 4 less than 5, it's correct. Right, so now if I square this on both sides, that means it will become x square less than y. Right, then if I take some other value, even it satisfies, after squaring it, it might differ. Right, so that's why for any inequality, we cannot simply square it on both sides unless we are sure that both the sides of the inequality are positive. So using that, basing on that condition, we are going to solve our square root inequalities. So let's start with solving this square root thing with an example here, square root inequality. So here comes the first one. So the basic thing, the basic condition here, what is the inequality given here? X plus 4 greater than 2 root of 4 minus x square. So there is only one way to solve a square root. We have to square it on both sides. But we cannot simply square the expression because here they are not numbers. Here they are given in terms of variables. Right. So that's why depending upon the variable, it might change. Sometimes inequality might change. For some values, inequality may not change. So that's why simply we cannot square it on both sides. But we can square this on both sides if we are sure that both sides are positive, which means 4 greater than 5. So if we know both sides are positive, then we can square it on both sides. To make sure both sides are positive, we have to bring the condition, which means for inequality, the first thing we will be having a condition. So how we will be deriving the condition here? So that will be the first step. So for any square root inequalities, to get the solution, the first thing we will be having here is to get a condition. So to get a condition, what will be the thing? So the first will be whatever the square root expression, that will be greater than equal to. So we already know that whatever the square root expression, that will be greater than equal to 0. That means 4 minus x square will be greater than equal to 0. So from here, if I multiply with minus, this will become x square minus 4 less than equal to 0. So if I expand this, so x plus 2 into x minus 2 less than equal to 0. So now I can apply my wavy curve method here. So one is minus 2 and the other is plus 2. So plus minus plus, so less than equal to. So here x belongs to minus 2 comma 2. Right, so this is for my square root. So 4 minus x square should be greater than equal to 0. So this, we know that this entire expression now becomes a positive expression. Yes or no? In the similar way, if this side of the inequality is also positive, then I can square it on both sides. So what will be the other thing here? I will be having, that is x plus 4 should also be a positive value, which means x plus 4 should be greater than 0, which means x should be greater than minus 4. So now to get the condition, I have to take the intersection of my both these conditions. Right, so both these intervals. That means I am having minus 4, minus 2 and 2. So for the first one it will be this and the second one greater than minus 4. That means, so the intersection is nothing but minus 2 and 2. So what is my condition interval here? My x belongs to minus 2 comma 2. That will be my condition interval here. Right. So once I get my condition interval, that means in this condition interval, whatever x values I will be taking, if I substitute in the inequality, I end up getting both sides of my expression will be always positive. If I have both sides of my expression always positive, then I can square it on both sides. Right. So let's just do that. So for square root expression, first thing we should get is a condition interval. So here for this, what is our condition interval? The condition interval here is x belongs to minus 2 comma 2 closed brackets. So now as we have our condition interval, so let's just square this square root inequality on both sides. So what happens if we square it on both sides? X plus 4 whole square greater than 2 square 4 minus x square. So there will be no change in inequality here. So x square plus 16 plus 8x greater than 4 into 4, 16 minus 4x square. So let me simplify. So it will be 5x square plus 8x and 16 will be become 0. And x I can take common. So here 5x plus 8. So what are the critical point guys here? My critical points will be, one will be 0 and the other will be minus 8 by 5. So again our wavy curve method, plus, minus and plus. So it is greater than 0. It will be the positive interval. So positive interval. So that will be x belongs to minus infinity comma minus 8 by 5. Right. Union. Here it's from 0 to infinity. So this is my solution of the inequality. But this solution will be valid until unless I having this condition. So what will be my final thing? My final will be the intersection of my solution of this interval as well as my condition. So let's take the intersection guys. So I am having 2 here. I am having 0 here. So this will be minus 8 by 5 will be somewhere here. And I'll be having minus 2 here. Right. So first one in between minus 2 and 2. So this thing. And the second one minus infinity to minus 8 by 5 and then 0 to infinity. So what is my combined intersection here? So x belongs to minus 2 comma minus 8 by 5. So minus 8 by 5 open brackets and minus 2 close brackets, union 0 comma infinity, 0 comma 2 where 2 is closed brackets and 0 is open brackets. So what is my final solution of this inequality? So here x belongs to minus 2 comma minus 8 by 5 union 0 comma 2. So this will be my solution of this square root inequality here. Right. So I hope you guys got an idea how to solve a square root inequality. So for any square root inequality, the first and foremost thing will be we have to get the condition interval. Right. So once we get the condition interval, then we can square the inequality. Square the square root inequality. So to get a condition interval, we will be taking the square root expression will be greater than equal to 0 and the other will be greater than 0. Then both the expressions, so both sides of the inequality will become positive. Right. So let me explain you with this one more example how we'll be getting the condition interval. So once we get the condition interval, the other thing will be you'll be doing the squaring and then you'll be finding the solution and then taking the final intersection. So let me do it until condition interval, and then further you can solve it. So here what is our square root expression to get the condition? So 2x square minus 3x minus 5. So this should be greater than equal to 0. So let's just solve it. So how can we do it? Minus 10 and sum should be minus 3. So we can take 5 and 2. So 2x square minus 5x plus 2x minus 5 greater than equal to 0. Then I can take x common. If I take x common here, it will be 2x minus 5. And similarly, if I take 2x minus 5 here, it will be plus 1 greater than equal to 0. Then it will be 2x minus 5 and x plus 1 greater than equal to 0. So here we are having 2 as the coefficient, right? So now what will be the critical point here? So to make it, because this should be coefficient 1, so how can we make it? So we can make it this by taking 2 common. So x minus 5 by 2, x plus 1 greater than equal to 0. So as it's a positive value, there will not be change in the inequality. So now let's take our minus 1 wavy curve method and then 5 by 2 here, right? So it's a wavy curve method. So plus minus plus, so greater than equal to, which is positive. So this will become x belongs to minus infinity comma minus 1. 1 will be included. Union 5 comma 2 till infinity and 5 by 2 will be included, right? So now with this condition of x, we are sure that the LHS of the inequality is positive, but we have to be sure that RHS also be positive. So how can we sure that? So RHS, so x minus 1 should be also greater than 0, which means x should be greater than 1, right? That means x belongs to 1 comma infinity. So now we have to take the intersection of these two intervals. That will be our condition interval, right? So let me take the intersection. So minus 1 and then 1 and then 5 by 2. So it will be minus infinity to minus 1 and then 5 by 2 to infinity, and this is 1 till infinity. So what is the common intersection here? That is, here x belongs to 5 by 2 comma infinity, where 5 by 2 is included. So here this will be our condition interval, right? So once we have the condition interval, that is x belongs to 5 by 2 comma infinity. So in this interval, if we take any x value, our inequality, the both sides of the inequality will be positive. So if we are sure that both sides of the inequality is positive, then what is our next step? Simply squaring on the both sides of the inequality, right? So let's just do that. So I hope you understand the thing here. I hope you understand the point here. So the thing is, you will be squaring on both sides. That means 2x square minus 3x minus 5 less than x minus 1 whole square. So let's simplify it. So 2x square minus 3x minus 5 less than x square plus 1 minus 2x, right? So let's simplify. So here it will be x square. So and then minus x and then minus 6 less than 0. So if we factorize, it will be x minus 3 into x plus 2 less than 0. Again wavy curve method, that is minus 2 and plus 3. So plus minus and plus, so less than. So here x belongs to minus 2 comma 3, both are open brackets, right? So this is our interval after squaring on both sides, but we have to take the intersection of our condition interval as well as this solution interval. So what is our condition interval? X belongs to 5 by 2 comma infinity, where 5 by 2 is included. So let's take a number line. So minus 2, 3, sorry, 5 by 2, right? First it should be 5 by 2 and then it will be 3. So here it is in between 5 by 2 and 3, and for it will be 5 by 2 to infinity. So what is the common intersection? That is x belongs to 5 by 2 comma 3, where 5 by 3 is closed and 3 is open. Right. So what is our final solution of this given square root inequality? So here x belongs to 5 by 2 comma 3. This will be the solution. That is our final intersection of our condition interval as well as the interval which we end up having after the squaring on both sides. Right. So this is how we'll be solving any given square root inequality. So first, for square root inequality, we should be getting the condition interval. After that, we can square it and then finding the solution. And at final step, we have to take the intersection of both the inequalities, which will end up giving our final answer here. Right. So I hope you guys get it here. So let's move on to the next one. So here there are few questions, so you can just take them as homework. So this question is related to our wavy curve method. To make you practice, I have just added few questions which are related to wavy curve method. So you can do it as homework. So if time permits, at last we can get back to here and just have a look here. If not, you can just do it as homework. And if you have any doubts and questions, you can let me know in our next session. So this is a wavy curve method and take it as a homework. And this is also similar question that is related to our wavy curve method. So make this also a homework question and give it a try. So we have finished our square root inequality. So now we are getting into our logarithmic inequality. Right. So how we'll be doing our logarithmic thing? So let me take a logarithmic function, that is y equal to log x to the base a. So as I mentioned, in this logarithmic inequalities, the base will be very, very important. So we already know that for any logarithmic, the base a cannot be equal to 1. This is a first and foremost condition. Base a cannot be equal to 1. And there are two more conditions for a. As a is not equal to 1, which means a can be greater than 1 or else a can be less than 1. Right. Less than in the sense it cannot be a negative value again. Right. Which means there are only two possibilities here. That means a can be greater than 1. If not, a can be in between 0 and 1, because a cannot be equal to 1 as well as it cannot be a negative value. Right. And what is the another condition? So this is the condition for our base. That means a can be greater than 1 and a can be lying in between 0 and 1. Along with that, for x, what is the condition? And x should be always greater than 0. Here also the same thing. X should be always greater than 0. Whenever we are having this AND operation, what we'll be doing? We'll be taking the intersection. That you guys are very, very familiar with that, because we have done so far many questions related to AND or those kind of wordings. Right. So this is the first condition for any logarithmic inequality, that is a will be greater than 1 as well as x greater than 0, and the other will be a is lying in between 0 and 1 and x greater than 0. Right. So now how the inequality will be changing for these two conditions? So that is the question here. Right. So whenever the a value is greater than 1, then the inequality of the logarithmic expression will not be changing. Right. So let's see that. So why? So if we take a logarithmic expression where the base is greater than 1, we supposed to have a graph something like this. Right. So this is my x values here and the corresponding log values here. So let me take a x1 here. So if this is my x1, what is the corresponding y value? So this is log x1 to the base a. And if this is my corresponding x2, what is my value here? This is log x2 to the base a. So here from this graph, you can say that my x2 is greater than x1 or not. According to our x-axis, x2 is backside. So the x2 is backside of our x1, which means that x2 is greater than x1. So for the same thing here, you can see x1 is before than x2, which means log x2 to the base a is again greater than log x1 to the base a, which means here, is there any change in the inequality? No, right? Which means whenever the base of a log function, if it is greater than 1, then we can say that there is no change in the inequality. That means if for suppose we are having a log function, that is log a to the log x2 to the base a is greater than log x1. So this can be solved by if we eliminate this log, and we can write it as x2 and x1, and there will be no change in the inequalities. If my base a is greater than 1, then I can take x2 greater than x1. Directly I can do it and simplify it. If it is greater than equal to, then it will become greater than equal to. Right. So there is one more case. That is if I have log b to the base a greater than equal to c. So here, even in this case, if my base is greater than 1, then I can rewrite this as b greater than equal to a power c. So even for this case, my inequality won't be changing, which means if you have an inequality in terms of log on both sides, then we can eliminate the log and we can write directly in terms of our variables, and there will not be any change in the inequality if a value, that is the base value, is greater than 1. And similarly for this also we can write without change in the inequality b greater than equal to a power c if the base is greater than 1, because you can predict that from the graph of our log x to the base a when a is greater than 1. So this is our first case, which means what we can remember, if the base value is greater than 1, there will not be any change in the inequality. So let's see what happens for the case 2. That means if our a lies in between 0 and 1. So that is our case 2. So a lies in between 0 and 1. Along with that, x should be always greater than 0. Right? So now for this, how will be the graph of the logarithmic function here? Any idea? So the graph will be looking something like this if the base is lying between 0 and 1. So it will be something like this. Right. So if for suppose I have taken my x1 here, then the corresponding log x1 will be here. So log x1 to the base a. Similarly, if for suppose I have taken my x2 here, then my corresponding value will be here. That is log x2 to the base a, which means here we can obviously say that x2 is greater than x1, but here log x1 is greater than log a x2. That means the inequality has been changed. So initially x2 is greater, but here for log x1 is greater, which means whenever the base value, if it is lies in between 0 and 1, there will be a change in the inequality. So let's see the cases here. So if it is a less than 1 and x greater than 0, there will be a change in the inequality. That means if suppose we are having a log function something like this, x2 greater than equal to log x1. If here a is lying in between 0 and 1, we can write this as x2 less than equal to x1 directly. Similarly, for this type of function, log b to the base a less than equal to c. If even here my base is lying in between 0 and 1, how can I write this? So b greater than equal to a power c. So my inequality will be changing. So by using these two operations and these two cases, like when what happens to the inequality when a greater than 1, and what happens to the inequality when a is lying in between 0 and 1. So these two cases we'll be taking here and applying and finding the solution of the logarithmic inequality here, right? So I hope you guys understood both of these cases. So the first one will be a greater than 1 and the second one will be a lies in between 0 and 1. Here no change of the inequality, but here inequality will be changing, right? So let's see how we can solve the question, solve the logarithmic inequalities using these two cases where a is greater than 1 and a is lying in between 0 and 1. So here comes the first question here. So for here we are having log 2 minus 3x by x to the base of 1 by 3 greater than equal to minus 1. So along with the base of a, we are having one more, that is our whatever the x value. So if we are having log a to the x is equal to y, first condition will be x greater than 0. Along with that we can have a greater than 1, or else it can be x greater than 0 and a is lying in between 0 and 1. So can you guys give it a try? So you can check whether a is falling in which of the following cases, and how can we solve this, and how can we start solving this question. Quickly, guys. So we have clearly seen how it follows when the base is greater than 1 and when the base is lying in between 0 and 1, whether the inequality changes or not. So here you have to just apply the condition. So if you observe, the given expression is in the format of log b to the base a greater than equal to c. So how we'll be rewriting this? So this will be b a power c. If a is greater than 1, inequality won't be changing. If a is lying in between 0 and 1, then inequality will be changing. But before getting into that, we are having one more condition, that is always the b value here should be greater than 0. So let's start with that, guys. So what is a given logarithmic function? Here 1 by 3. The base is 1 by 3, which means it is lying in between 0 less than 1 by 3 less than 1. So inequality will be changing. Along with that, what is the second case? That is our b value should be greater than 0, which means 2 minus 3x by x should be greater than 0. So to make this positive, I am multiplying with minus. So 3x minus 2 by x. So inequality will be changing as I have multiplied with minus 1. So now what are my critical points here? One is 0 and the other one is 2 by 3. Right. So I have to make it 1 coefficient of x. So I'll be taking 3 common. This will be x minus 2 by 3. And here x less than 0. I am dividing with by 3. Then it will become x minus 2 by 3 divided by x less than 0. So now here I can apply my wavy curve method. So what are the critical points, guys? So one is 0 and the other one is 2 by 3. It will be somewhere here. So it will be plus, minus and plus. So here it is less than 0. So it will be negative. So here x belongs to 0 comma 2 by 3 open brackets. Right. So this is my condition which I end up having for my inside expression of log greater than 0. So now I have to solve my exact logarithm inequality and then I have to take the intersection of both these conditions. So let's solve the second condition. So here this is a is lying in between 0 and 1. So it's obvious that inequality will be changing. So if it is log b to the base a greater than equal to c, we'll be writing b inequality changes, so less than equal to a power c. That means b here 2 minus 3x by x less than equal to, a here will be 1 by 3, c will be minus 1. So this will be 2 minus 3x by x less than equal to 3 power minus 1, that is plus 1, so 3. Right, so this will be further simplified. 2 minus 3x by x minus 3 less than equal to 0. If I take x as LCM, 2 minus 3x minus 3x less than equal to 0. So 2 minus 6x by x less than equal to 0. So to eliminate the minus, it will be 6x minus 2 by x greater than equal to 0. But I have to make my coefficient of x here to be 1. So I'll be taking 6 common. So I'll just erase this, guys. So far we are having the simplified 6x minus 2 by x greater than equal to 0. So 6 I am taking common. So x minus 2 by 6 by x greater than equal to 0, which implies x minus 1 by 3 by x greater than equal to 0. So again we can apply the wavy curve method, 0 as well as 1 by 3. So plus, minus and plus. So here greater than equal to 0, isn't it? So if it is greater than equal to 0, what will be the interval? X belongs to minus infinity to 0, where 0 is included, union 1 by 3 comma infinity, where 1 by 3 is included. So what is our previous interval which we get by taking the inside expression greater than 0? There x belongs to 0 comma 2 by 3. So now we have to take the final intersection here. So 0, and then we are having 1 by 3 and then 2 by 3, right? So it will be 1 by 3 and then 2 by 3. So for the first it will be 0 and 2 by 3. So this will be the thing. And here minus infinity to 0. So this the thing. And the next one 1 by 3 to infinity. So this will be the thing. So what is the common intersection we are having? That is 1 by 3. So here x belongs to 1 by 3 comma 2 by 3, where 1 by 3 is closed and 2 by 3 is open. So what is the final solution of this logarithmic inequality here, guys? So the final solution is given to be x belongs to 1 by 3 comma 2 by 3, where 1 by 3 is a closed bracket and 2 by 3 is a open bracket here. Right, so I hope you guys followed this. So for all these square root expression like square root inequality, logarithmic inequality, we will be having more than two solutions or two or more than that. Then we have to take a final intersection to get the ultimate and final solution of that corresponding inequality. Right. So here we have done for one logarithmic question. So let's just solve one more question, guys. So can you guys give it a try? So I have given the question here. Quickly, can you guys give it a try? So here if you observe, there are two logarithmic expressions, which means this expression should be greater than 0, one condition, and this expression should also be greater than 0, two conditions. And then you have to take the intersection. And then you have to follow this logarithmic condition with respect to the base, and you will be having one more interval, which means overall we will be having 3 final intervals, and at last we have to take the ultimate intersection of these 3 intervals, and that will be the final solution. Quickly, can you guys give it a try? So see here, guys, what is the expression which is given here? So whatever the logarithmic expressions, the inside expression should be always greater than 0. So we'll be starting with 2 minus x should be greater than 0. then it will be x minus 2 less than 0 and x should be less than 2. So one condition. And what about the other? 2 by x plus 1 should be greater than 0. So here if you observe, it is in the form of numerator as well as the denominator. So we can see that numerator is a positive value 2. Right, and here it is greater than 0, which means if this is positive, to have this entire expression greater than 0, even the denominator should also be positive. Right, which means x plus 1 should also be greater than 0, from where we get x should be greater than minus 1. So two conditions here. One is x greater than minus 1 and the other is x less than 2. So now as we have get the two conditions, so what will be the next condition here? So the next condition will be simplifying the logarithmic expression. Right. So here what is the base here? So the base for this logarithmic expression is 1 by 4, which is lying in between 0 and 1, which means there will be a change in the inequality. So then this expression will turn out to be 2 minus x. So here it's a greater than. So as the base is lying in between 0 and 1, inequality will be turning out to be less than and 2 by x plus 1. So let's simplify this. So 2 minus x minus 2 by x plus 1 less than 0. If I take the LCM here, it will be x plus 1, 2 minus x minus 2 by x plus 1 less than 0. Right. So we can simplify this further. So it will be 2x minus x square plus 2 minus x minus 2 by x plus 1 less than 0. So plus 2 and minus 2 will be getting cancelled, and then 2x minus x will be x. That means minus x square plus x by x plus 1 less than 0. So here if I suppose to take minus x common, then it will be x minus 1 here by x plus 1 less than 0. So here I am having this minus, so I have to eliminate this minus. Then the inequality will be changed into x minus 1 divided by x plus 1 greater than 0. So now I can apply my wavy curve method. So what are the inequalities here, guys? So I am just doing the number line thing here. So let me adjust this. So let me draw the number line here. So here, what are the critical points? 0 and then 1 and then minus 1. So what are the previous critical points? That is 2 here and then minus 1 here. So 2 also will be added. So I am just taking the final intersection so that we can get the final answer. So for the first, it will be x will be less than 2. That means less than 2. Okay, let's just simplify it. I'm just erasing this entire part so that it won't be confused. So first condition x greater than 2, second condition first condition x should be less than 2, right? So first condition x less than 2, second condition x greater than minus 1, and the third condition we are having is x minus 1 by x plus 1 greater than 0. So first we'll apply the wavy curve method here. 0, 1 and minus 1. So it will be plus, minus, plus, right? So greater than, which means it will be plus, that is minus 1 and 0 union 1 comma infinity. So plus minus plus and this will be minus, right? So that's why it will become minus 1 to 0 union 1 comma infinity. So this is the solution from the logarithmic simplification. So now we have to take the entire intersection. That will be minus 1, 0, 1 and 2. So less than 2, first condition, entire thing. And second condition, greater than minus 1, entire thing. And next one, minus 1 to 0. I'm just doing it like this. So minus 1 to 0 until here, and then 1 to infinity. So what is the intersection of these three intervals? That is nothing but first this part, that is minus 1 to 0, x belongs to, and the second part will be only this part because this is not the intersection of the other. So union 1 comma 2. So what is the final solution of this logarithmic inequality, guys? So the final solution here, the x belongs to minus 1 comma 0 union 1 comma 2. So this will be the final solution of the logarithmic inequality, right? So this is how we'll be simplifying our any of the logarithmic inequality of this type. So let's move on to the next one, guys. So here comes the next inequality, which is nothing but the exponential inequality. So as I mentioned, for exponential inequality, so there is nothing new here. So what will be the basic expression? So y equal to a power x. So here again, how the base initially dependent for the logarithmic, here the a will be again dependent. That means we'll be having again two cases. So a will be greater than 1 and a will be lying in between 0 and 1. And the conditions will be the same thing for in between 0 and 1 inequality changes. That means sign of inequality changes. Same conditions. And here no change of inequality. No change of inequality. Even in the logarithmic thing we had the same thing. So if the a is greater than 0, there will not be any change of inequality, any change in the sign. If the a is lying in between 0 and 1, then it will be obviously there will be a change in the sign of the inequality. So the same conditions which we have applied for our logarithmic inequality will be applicable even for the exponential inequality here. So let's try and solve questions related to exponential inequality, guys. So here comes the first question. So can you guys give it a try? How can we actually try and solve this exponential inequality? Any ideas? Can anyone give it a try at least? So the first and foremost thing will be our a value should be same. So that's the thing, we have to make it same. So if my y equal to a power x, so let's try and make the a of the two sides of the exponent should be equal. So that will be our first step. So how can we make it equal? What is the given inequality? 2 by 5, 6 minus 5x by 2 plus 5x less than. So 25 is nothing but 5 square and 4 is nothing but 2 square. Can I write it like this? 5 by 2 whole square. But here this a is 2 by 5 and here it is 5 by 2. So I can convert this 2 by 2 to 5 by 2. Yes or no? How can I convert? By making the power minus. That means 5 by 2. So there will be a minus sign. If I multiply with the minus, so minus 6 minus 5x by 2 plus 5x less than 5 by 2 whole square. So now if my power is same, that is my a value is same. So here let's see whether this a value is greater than 1 or not. So it is greater than 1 because 5 by 2 is nothing but 2.5, which is greater than 1, which means there will not be any change of the sign. That means it will be minus of 6 minus 5x by 2 plus 5x less than 2. Right, so let's simplify this. So 5x minus 6 by 2 plus 5x minus 2 by 1 less than 0. So let's take the LCM here. So 2 plus 5x, 5x minus 6. So minus 4 minus 10x less than 0. So then it will be minus 5x minus 10 by 2 plus 5x less than 0. Right. So let me take minus 5 common here. So I can take minus 5 common, and it will be x plus 2, and here it will be 5x plus 2 less than 0. So now I have to eliminate this minus 5. So I am going to divide with minus 5. So if I am dividing with negative value, in the sense there will be a change in the sign. So let me erase this, guys. So now I am having minus 5x plus 2 divided by 2 plus 5x less than 0. So I have to eliminate this minus 5. So I am dividing with minus 5. So there will be change in my inequality. So it will become greater than 0. So again I have to take this coefficient 1, make it coefficient 1, so that I can apply my wavy curve method. So x plus 2, so x plus 2 by 5 greater than 0. So now number line to apply the wavy curve method. So minus 2 and minus 2 by 5. So minus 2 and minus 2 by 5. So wavy curve method plus minus plus. So here the inequality is greater than 0. So it will be a positive sign. That means minus infinity to minus 2 union minus 2 by 5 to infinity x belongs to. So this will be my final solution of this exponential inequality, and this will be my final answer. So here what is the thing? So my x belongs to here minus infinity to minus 2 union minus 2 by 5 comma infinity. So if we compare with the logarithmic, exponential inequality solving is very easy, right? So let's just do one more question related to exponential, and then we'll jump into our final inequality, that is trigonometric inequality. So here comes the next question, guys. Can you guys at least start solving this one quickly? So same procedure you can apply here. You can take the same methodology and you can simplify this exponential inequality. So what is the given inequality? 3 power x plus 2 greater than 1 by 2 power 1 by. So first thing will be, we have to make the a value same on the both sides to simplify the exponential inequality. So how can we do that? Here it is 3. So we cannot make 3 to 9, but we can make our 9 to 3 easily. So comparatively making 9 to 3 is easy because 9 can be written as 3 square. So 3 power x plus 2 greater than 3 square can be written as 3 power minus 2 into 1 by x. That means 3 power x plus 2 greater than 3 power minus 2 by x. So here what is our a value? This is greater than 1. Then there will not be any change in the sign of the inequality. So now how can we write it? So x plus 2 greater than minus 2 by x, and simplify it easily. So let's just do that. So x plus 2 plus 2 by x greater than 0. So if we take LCM, so x square plus 2x plus 2 divided by x greater than 0. We have to factorize the numerator. So how can we write this? So x square plus 2x plus 1 plus 1. So 2 can be split as plus 1 and plus 1, and this term can be written as x plus 1 whole square plus 1 by x greater than 0. Right? That means what are the critical solutions here? You can see. So this x plus 1 whole square. So here it is not entirely factorized. So we cannot apply the wavy curve method. But here what is the expression we are having? That is x plus 1 whole square plus 1 by x greater than 0. So here if you see, whatever the x value we can substitute here, as it's the square, this thing will be positive. And plus 1, which means the numerator which is given here is anyways positive, right? So if the numerator is positive and the sign here is greater than 0. So when it is possible, if the numerator is positive as well as the sign should be greater than 0, then the denominator should also be a positive, which means what is the variable in the denominator? X. So x should also be positive, which means x should be greater than 0. That means what is our solution? X belongs to greater than 0, which means 0, infinity. Right. So the final solution of this exponential inequality is nothing but x belongs to 0, infinity. So how we have obtained and solved this? So let me show you a standard thing. So if for suppose we are having a fraction a by b which is greater than 0. So what are the possible cases? So both can be positive or else both can be negative. Right. So in the previous case we are having x plus 1 whole square plus 1 by x greater than 0, which means this is a square, so this will be positive. So x plus 1 whole square will be positive, plus 1, so that will also be positive, which means I end up having my numerator is positive. And when I will be having a greater than 0 term, if my denominator also be positive, that means my denominator is having x, so that should also be positive, which means x should be greater than 0. That means my solution will be x belongs to 0, infinity. This will be my final solution here for the given exponential inequality. Right. So far we have done our square root inequality, logarithmic inequality, exponential inequality. So now let's get into our next one, that is trigonometric inequality. So for this trigonometric inequalities, so we should be aware of our trigonometric solutions, that is general solutions. So if you guys remember, so what will be the solution? Sin theta equal to sin alpha. So we have already seen theta will be equal to n pi plus of minus 1 whole power n alpha. So we have seen in our trigonometry chapter. So similarly, when cos theta equal to cos alpha, theta will be equal to 2n pi plus or minus alpha. Right. Similarly, for tan theta equal to tan alpha, what is my solution? Theta will be equal to n pi plus alpha. So here these are our solutions for trigonometric equations. But whereas here we are trying to solve the inequality. So this equation solutions will be obtained to make the generalized solution. But we have to get the final answer. We will be solving it by using the graph of the trigonometric inequality. So let's just understand and see one question related to our trigonometric inequality so that you guys have idea how to simplify it and how to solve any trigonometric inequality. So here comes the question, guys. So what is the inequality which is given here? Cos x greater than equal to minus 1 by 2. So first let us take equal to. So cos x equal to minus 1 by 2. So what is the x value when angle equal to minus 1 by 2, when cos x equal to minus 1 by 2? What is the theta value? It is x will be equal to 120 degrees. That is nothing but 2 pi by 3. Right. So not only it will be one side, because we will be having both sides of the graph. So if I take my sine graph, so 0 here, I'll be having something like, so let me take minus 1 by 2 here, guys. Right. So I'll be just dropping my graph here. So I'll be having my sine graph something like this. What is my 0 here? So my sine 90, that is pi by 2, will be 0. And similarly, minus pi by 2 will also be 0. And this is 0. And this is my y-axis, that is minus 1 by 2. So what will be an angle when it is minus pi by 2? So somewhere here. So the angle at this point, that is the x value, will be 2 pi by 3. Similarly, I will be having for the other side. So that is nothing but here somewhere, that is minus 2 pi by 3. So first thing, to solve this trigonometric inequality, we have to get that exact points on the graph. Right, so here the inequality which is given here is cos x greater than equal to minus 1 by 2. So I have taken that x by x value which is 120. So this is 1 point and this is 1 point. And here it mentions it is not, we don't want the solution at exactly equal to that, but it should be greater than and equal to, which means the graph should be greater than. So what is the upper graph? So here like this will be having, so from this point to this point, the greater graph, which means this is the graph which is greater. So this entire graph is nothing but greater until here. So what will be my solution here? So my x will be lying in between minus 2 by 3 less than equal to x less than equal to 2 pi by 3. So for this inequality, what is the solution? Minus 2 pi by 3 less than equal to x less than equal to 2 by 3. So it's as simple as that. If in case it is less than equal to, then this graph, so it will be this part. Right, so it is greater, so that's why we'll be taking this shaded region, which is minus 2x will be lying in between minus 2 by 3 to 2 by 3. If we want to get a generalized solution for this, so here it is related to cos theta equal to cos alpha. So what is the generalized solution then? 2n pi, which means for this my x will be belongs to 2n pi minus 2 pi by 3, comma, so let me write it. Okay, let me write it here. So my generalized solution will be x belongs to 2n pi minus 2 pi by 3, comma 2n pi plus 2 pi by 3. So this will be my generalized solution because this will be included. So closed brackets. Right. So this will be the regular solution. We can say principal solution. But if we want to write the generalized solution, we'll be picking up from that our cos theta equal to cos alpha, and this will be our generalized solution. So it would be easier and it will be very important to take the graphical method while we are solving any trigonometric inequality. Right. So that's all, guys. So we have discussed about our all types of inequalities, all the properties involved. So especially we have discussed in today's session square root inequality, logarithmic inequality, exponential inequality, as well as the trigonometric inequality. And in entire this linear inequalities chapter, we should be very careful with the properties as well as the different inequalities we have seen, and you have to be very handy with the wavy curve method, because by solving and finding the solution using wavy curve method, it will be very easy, right? Because even to find the solutions of these types of inequalities like logarithmic, exponential, in that also we are actually using our wavy curve method. So with this all types of inequalities we have finished. We have covered all the concepts clearly in this entire chapter of linear inequalities. So with this we are finished with the chapter of linear inequalities, guys. So in our next session we are going to start with a new chapter. So you guys, some questions I have given you as homework, so keep trying it. So please do that homework, and if you have any questions after solving the homework questions and all, you can get back to me in the next session and we can have a discussion and clear out all of your doubts. Right, so that's all for today. So let's meet in our next session with a new chapter. Thank you.